Welcome everyone to the second season of MOS Mathematical Online seminar series organized by EMEA. And as you know, EMEA is part of EMS. So if you are not member of EMS yet, we encourage you to check the info on how to join it in this QR. So Christina and I are very happy to be here today, and I am first going to introduce what this seminar are. First, due to the success of the first edition organized by Christina and Elena, MOS continues to bring together leading young academics in mathematics from around the world. So the idea of these seminars is that they are accessible to a broad audience, regardless of the specific field of the attendees. So most importantly, we want these talks to be inspiring for the upcoming generation of young mathematicians. We will have a talk every first Thursday of each month from now to Jan, and each talk will last about 40 minutes plus a Q&A. Here you have the QR to register to the mailing list to be tuned of the following talks, and also when the recorded video are available in the EMS YouTube channel. So this is the schedule of the second season, and as you can see, all the speakers have exceptional trajectories, and they have been awarded with several prizes. So now it's time for Christina to introduce Danylo, who is our next speaker and the first one of this season. And I hope you like a lot this presentation. So
thank you very much.
Well, no. Okay.
Thank you very much, Belém, and welcome everyone to the second season. We are very happy to have you here. So, well, I will present Danylo. Danylo Radchenko is a CNRS researcher working at Laboratoire Paul Painlevé at the University of Lille, France. He did the Bachelor in Mathematics at Taras Shevchenko National University of Kiev, Ukraine, and the Master at the University of Manitoba, Canada. He obtained his PhD in 2016 from the Max Planck Institute for Mathematics and the Bonn International Graduate School for Mathematics in Germany, and has served as postdoc in Italy, Germany, and Switzerland. His research interests include modular forms, algebraic number theory, convex and discrete geometry, combinatorics, as well as approximation theory and Fourier analysis. He has published 37 papers and has 9 preprints, and he's recipient of the EMS Prize awarded in 2024, the CNRS Bronze Medal also in 2024, and the European Research Council Starting Grant in 2022. As it could not be otherwise, it's a great honor for us to have you with us today. We truly appreciate you taking time out of your busy schedule to be with us and share your insights today on sphere packings and modular forms. So the floor is yours, Danylo.
Thank you very much. Can you hear me?
Yes.
Yes, okay.
Yeah.
And also, do you see my screen?
Yes.
Yeah.
Okay, that's a good start. So I haven't done this in a while, so if something breaks, please tell me. It's a great pleasure for me to give this talk. I selected a topic which I kind of both know well, I worked on, and I find it very beautiful, and it is the kind of the most surprising appearance of modular forms that I know. At least, well, it's a candidate for the most surprising appearance in mathematics in period. And actually, what I like about the stories is that modular forms surprisingly appear twice. well, once they appear in a classical way and in a way that people have noticed maybe 100 years ago, but the second appearance is a little bit stranger. It's kind of a backdoor appearance, but it plays an equally important role in the story. So, but I'll kind of, I tried, so the story is a little bit general in the sense that it includes parts of geometry, analysis, number theory, and there's a lot of things connected to it. On the other hand, I'll try to keep all of the technicalities away. And in general, you're not expected to know anything, or at least you have to know at least something in the sense that you have to have heard of it. But otherwise, I'll try to keep things relatively on the surface. Okay. So let me start, and already I'm having a little bit of okay, now this works. So the sphere packing problem is the kind of main topic of today's talk. And it's a very simple problem to state. And like many other combinatorial geometric problems, it's easy to state, but it's very hard to solve. But it has some kind of, not all combinatorial geometric problems are equally interesting. And there's no doubt that sphere packing is an interesting problem just by the account of how many different areas of mathematics it kind of pulls in. Okay, so but the basic problem is you want to arrange equal size spheres in a Euclidean space of some dimension, and you want to arrange them in the most economical way in the sense that you want to pack as many spheres in a small volume as you can. Or if you think a bit the other way, you want to cover as much of the space with your spheres while not allowing them to overlap. Okay. So in fact, it's actually the question about solid spheres, not the actual codimension 1 spheres, but the name stuck, so everyone calls it a sphere packing. And just to make it a little bit more precise, so what are the two quantities we're interested in? So we have some subset of centers of spheres we're trying to locate, and it's the subset of the Euclidean space of dimension d, which I'll call C for configuration. And there's two quantities that we're interested in that kind of govern the whole problem. So one quantity is telling us how close the points are together, and that's the packing distance. So that's the minimal distance between the points of your set C. And the other quantity is the center density, which tells you roughly how many points you have per unit volume. So in fact, you don't have to think about these precise definitions at all. So any kind of rough idea of what these two quantities are will suffice. So I'll never actually try to prove any statements here. But roughly the sphere packing problem asks for kind of two different questions, but they end up being equivalent. So one of them is you fix the packing distance. In other words, you fix the minimal space between points that you have, and you try to maximize the density of the centers. And the other way to think about it is you do the opposite. You fix the density, and then you try to push points as far as you can. And it's not hard to convince yourself that both problems are the same. The answer to one gives you the answer for the other. And in fact, there's an additional freedom in choosing the size of your spheres any way you like, because in Euclidean space you can rescale, and like metric questions are essentially preserved. Okay, so this is kind of a bare bones statement of the problem. So what I want to do now is give a little bit of illustration of what's going on. So if you think about one-dimensional problem, there's not much to do. It's very boring. But the interesting things start already in dimension 2. So if you try to arrange things on a plane, it seems pretty convenient to have some kind of periodicity. And among periodic configurations, it's almost immediate to come up with the one which is looks like it's the densest. And this is the hexagonal lattice or triangular lattice, not to be confused with the honeycomb lattice, which is not a lattice. But in any case, it is the way the honeycombs are arranged in nature. And the only question is here. The answer is easy to guess. The proof is actually not so easy. And I will not talk about either this case or the next case, which is quite a bit more interesting, three-dimensional case. So three-dimensional case is a very famous problem that was open for 250 years, maybe more. It's so-called Kepler's conjecture. And it asks precisely the sphere packing problem in dimension 3, so which you can think of as you're trying to pack oranges in a crate in the most efficient way. So once again, guessing the answer in small dimensions is usually very easy because we have a lot of experience from everyday life. So what you kind of do is you start with the solution you already have in dimension 2, and you try stacking it on top of each other. So, so it's kind of easy to see that you can stack in a nice way two solutions. And then you can do the third one. But there's kind of some hidden problem here where, in fact, it's a little bit hard to see from this picture. But if you look at the two-dimensional picture and look at where the holes are in your packing, there's two types of holes, in the sense that the holes themselves are invariant under the translation of the same lattice you start with. And so on the picture, I have green holes and the red holes. And there, you can get from green to green by translation by vectors from your lattice, and you can get from red to red, but not between the colors. And so what this means practically, so in this process that we had on the previous slide, when we were stacking things, at each step you have a choice. So you can either choose, starting from layer 1, which is blue, you can either choose green or red. And then on the second step, you can kind of again have to make a choice, but now you cannot choose green, so you have to choose either red or blue. And as you go up, you kind of have to make infinitely many choices. So if you think about what happens in the dimension of layers, it's essentially one-dimensional problem, and you're just coloring points like integers, which tell you the number of the layer you're on. You're coloring them in 3 colors, and the only condition they have to satisfy is that the consecutive colors are different, and that's it. And it's not that hard to see that there actually is a ton of ways of coloring integers in 3 colors, and each one produces a packing, and most of them are not isometric. So already in dimension 3, even this naive procedure produces infinitely many candidates, and all of them have the same density. And in fact, all of them are best packings, as we now know. So a 3-dimensional problem is several orders of magnitude more difficult than a 2-dimensional problem. And this kind of sequence is so bad that the 4-dimensional problem, if you try to attack it in the same fashion, it seems pretty hopeless. Okay. So, so let me give you some table which contains most of what is known about the sphere packing problem. So one caveat is I will only talk about exact results. There's quite a lot of results which are also very interesting about the behavior of this problem in large dimensions. So so-called asymptotic questions. So I will not even mention them, even though it's a very interesting topic. So just be aware that I'm kind of selectively talking about the sphere packing problem. So in dimension 1, as I said, there's nothing to prove. In dimension 2, it's the first picture I showed you. It's the so-called A2 lattice, or triangular lattice, or hexagonal lattice. And so depending on how strict you are to like the level of rigor in mathematical proofs, there's several proofs in the literature, starting from Thue from late 19th century, to Weierstraat, whose proof is certainly completely rigorous, and it's around 1940s. And there's a lot of names I'm kind of omitting because I am actually not, so the talk is not supposed to give a very accurate history. I'm doing what I can. And so in dimension 3, the story is there's infinitely many configurations. One of them is a lattice, and it's a so-called A3 lattice from the classification of Dynkin diagrams. And it's exactly the one that you get from the stacking process if your sequence of colors is periodic. So if it has period 3, what you get is a lattice, and that's exactly the A3 lattice. And the fact that all of these constructions are optimal was proved by Hales only, well, at the end of 20th century. And there's 2 dates here because both proofs are extremely difficult and they're also computer assisted. And so the original proof of Hales was computer assisted, but not in a strict. So the computer assisted parts were not rigorously verified. And the second date is actually the formal proof verification that everything actually is okay. But unfortunately, it's impossible to understand the whole of the proof by a human. So even though we more or less believe that everything is correct, it's a little bit too complex. And so the story would be kind of sad and boring if it ended here. And the surprising part comes from the work of Marina Wiazowska from 2017, who managed to prove that actually in dimension 8 we can also solve the sphere packing problem. And it's again given by a nice periodic structure, which is called the E8 lattice. And shortly after that, it was kind of realized that her proof also can be modified to work for another lattice, which is even more exceptional than the E8 lattice. It's a 24-dimensional beast called the Leech lattice. And unfortunately, I will talk a little bit about Leech lattice, but not even close to enough to give it kind of the due credit. So it's a fantastic mathematical, one of the most fantastic mathematical objects in the sense that it has so many properties holding for it that by all kind of reasonable criteria, it should not exist, but it does. And the fact that it does kind of helps solve the sphere packing dimension 24 dimensions. And that's essentially the end of the story as it exists now, in the sense that we have a lot of candidates for other dimensions, but we don't have any kind of good proof strategy. Okay. So what am I going to talk about next? Let me first say a little bit more about a version of sphere packing problem where we kind of put more restrictions on the centers of the spheres. And so what one can notice is that in the short table that contains all of the exact results we have, all of the solutions, well, at least one of the solutions is always a lattice. And in fact, it's kind of special. So it's something most likely having to do with small dimensions. And there is, unfortunately, very little in terms of rigorous heuristics we can provide. But most people believe that this only happens in dimensions which are very small, or if something very exceptional happens, like in dimension 24, we have the Leech lattice. And in general, this shouldn't be the case that the best packing is a lattice. Well, at least, I mean, I'm part of the experts who believes that this is not the case in high dimensions. But what is always expected is there should be at least one solution that we can describe in simple terms, namely there should be one periodic solution. And this is a conjecture by Zassenhaus, and despite how simple it sounds, it actually seems pretty nasty. So there's almost nothing one can say in support or against it, and it's a very strange situation, but that's what we have to live with. Okay. So by the way, if there are questions, very important questions during the talk, if something is completely unintelligible or you can't understand anything, feel free to interrupt me. Okay. So what I want to say now is give a small overview of what is known for so-called lattice packing. And so the only reason why I want to talk about it is because actually very rarely that there are new things are proved about the sphere packing problem, especially in the exact kind of sense. And last year was kind of an exception. So I want to mention that. So if you look at the lattice packing problem, which means you try to solve exactly the sphere packing problem, but you restrict your centers to form an additive subgroup of RD. Then the problem is even more classical in a sense than Kepler's problem. And it's essentially equivalent to some questions about quadratic forms. And people studied it for a very long time. And the results go back to Lagrange, Gauss, Korkinen, Zolotaryov, and Blichfeld. So in fact, all of the dimensions up to 8 were done before 1930. So before actually anyone had access to any computers. Well, other than human computers, of course. But so the next two cases are kind of a little bit strange. So the next case actually is not 9 by 24, and that was the work of Kohn and Kumar, who proved before Vezovska's work. They already proved that the best lattice packing in dimension 24 is the Leech lattice, and the proof is a little bit computational. So it's not like something you could easily do without access to any computer, although in principle it is doable. And the proof in dimension 9 is kind of completely computational, but that's last year's work by Mathieu Dutour-Sikirich and Van Woerden. And it's a pretty impressive tour de force of computational power that people have now have. It's also, again, very hard to kind of conceptualize. So even though we know the best lattice packing in dimension 9 now, the only reason why we know it is because of a huge computational effort. Okay. So, oops. What I wanted to say actually is that this table for lattice packing should actually be at least contain all the answers for the actual sphere packing problem. And that's the conjecture of Conway's law. So at least up to dimension 8, we should be actually in good hands, in the sense that we should know what the answers are. It's just that there is no good way of proving it. So for the rest of the talk, I'll only talk about the two cases where the proofs are actually using completely different ideas. They're not very geometric, and they're they're completely understandable by humans. That's kind of the good part. So I want to maybe just spend a little bit of time to introduce the two lattices I will talk about. And I will mostly talk about the E8 lattice. And its definition is extremely simple. It doesn't quite tell you why it's such a nice object, but the definition is you just take all vectors in R8, whose coordinates are either all integers or all half integers, and you only require the sum of coordinates to be an even integer, and that's it. So what you get is a lattice that's easy to prove. It has some other properties that I'll mention in a moment, but it turns out to be kind of very special. And in fact, well, the special part comes from the classification of Dynkin diagrams, but I won't go into that direction at all. So it has a kind of big brother, which is a Leech lattice, which doesn't appear in the classification of Dynkin diagrams. And in fact, the fact that we know Leech lattice existence is directly connected to the sphere packing problem. So it was discovered exactly as an attempt to solve the sphere to find a very good packing in 24 dimensions. And unfortunately, there's like no very easy way to describe it, which is also kind of well, both understandable and kind of conceptual. The easiest way is the following, which was, I believe, discovered by Conway. So you don't start with a lattice in dimension 24. You start with something a little bit stranger in dimension 26. So you start with a lattice which is constructed exactly the same way as above, but it lives not in a kind of positive definite metric space, but it was in R26 equipped with a Minkowski type inner product. So it has signature 25(1). And there's kind of strange numerology going on, but what you can see is, well, the construction is very simple. So you take these two vectors, u and v. So one is just all consecutive integers up to 24 and then 70, and the other is just with first two coordinates permuted. So it's kind of very easy to describe. It's very hard to see why this is a good choice. So the construction of the Leech lattice is then you just take the orthogonal complement of these two vectors in the 26-dimensional space. And kind of the weird numerology here is the following. So if you take this inner product with signature 25(1) and you compute the norms of the vectors u and v, actually they're both isotropic, meaning that their norm is 0. And there's a number theoretical fact hidden here, which is if you take the sum of squares of the first 24 integers, you get a square. And this actually, the only interesting case in which it happens is for 24. So that's the strange numerology at work. And don't ask me to explain why this works this way or how it works. It's just how things are. Unfortunately, I don't have a kind of good understanding of why these things exist, but sometimes miracles happen. What I want to say is, so now we switch a little bit to kind of Fourier analytic part of the talk, and I will not do any heavy Fourier analysis. But what I want to say is there's a very useful part of Fourier analysis that allows you to understand geometry of lattices well. Just for completeness sake, so recall what a Schwarz space is. So we're just looking at all nice test functions on RD, meaning they're smooth and their all derivatives are of rapid decay. And on this space, Fourier transform is well defined, and it's in fact an isometry. But I'll only kind of use very basic properties. So the Fourier transform is just the integral of f against the character. Okay, so far so good. It's again a function in the Schwarz space. And so what one can do, so I'm trying to get at Poisson summation formula, and to define it in the classical case is very easy, but if you want to define it in high dimensions, you have to be a little bit careful. So the nice way of defining it is to take a lattice and consider its dual lattice, and also consider the covolume. So it turns out that kind of the natural formulation of Poisson summation formula is completely intertwined with theory of lattices, in the sense that it just tells you that if you sum your function over the lattice, the answer is the same as summing the Fourier transform of your function over the dual lattice, up to normalization. So this will kind of give a lot of non-trivial things. So one thing that is the classical entry of modular forms into the story is, well, which kind of functions we can take to get some interesting information about the lattice. For many problems in Fourier analysis, the most interesting function actually is the Gaussian. And in this story, it's important because the Fourier transform of the Gaussian is the Gaussian itself. So this you can verify, well, it's not a completely trivial statement, but it's relatively straightforward. And so if you take Gaussian and plug it into Poisson summation formula, on both sides we'll get sums involving Gaussians. And it's convenient to organize all of this information into a generating series. And the generating series is the so-called theta series of the lattice lambda. So by definition, it's just the sum of the Gaussian with parameter tau over the lattice. And the point of view is you think of it as an analytic function of tau in the upper half plane. Okay. So because if tau is in the upper half plane, these functions all rapidly decay, all of the sums are convergent, everything is fine. And the Poisson summation formula simply tells you a simple transformation rule between the theta functions of lattices and their duals. So it tells you that the theta function of the lattice at the point tau is essentially equal to the theta function of the dual lattice at the point -1 over tau, up to this kind of normalization factor. And so this is kind of very useful. So for example, even though I gave you the definition of the E8 lattice, it's very hard to get anything more precise than that just by knowing the definition. But it's relatively easy to check several properties of this lattice lambda 8. So first of all, it is unimodular. It is even, meaning that squares of lengths of any vector in this lattice are even integers. And as a corollary of these two properties, also self-dual. So this you can just do as an exercise. It's quite easy. But now in combination with the previous discussion, what you get is if you look at the theta function of the E8 lattice, it satisfies two transformation laws. So first of all, it satisfies this transformation law is involving -1 over tau, and that's precisely the Poisson summation formula. So that's what we were talking about. But actually, it's just by its very definition, it has an additional transformation rule, and that's its periodic. It's one periodic. And this is precisely because the lattice lambda 8 is even. So sorry, here it should be lambda 8 in all 3 points. And because it's even in the definition of the theta function, you only have powers of integer powers of 2 pi I tau appearing in the exponents. So they're all periodic functions of tau. So it turns out that actually these two properties uniquely determine the function g. The reason for that is because if you start iterating these properties, you get that g is in fact what is called a modular form of weight 4 for the group SL2Z. And what this means in practical terms, so without going into precise definition, is G satisfies a very strong transformation property. So if you apply any fractional linear transformation with integer coefficients to G, you can compute it in terms of the values of G before you apply it. And then the theory of modular forms tells you that in fact, the space of functions which satisfy this transformation property, together with a certain restriction, which is satisfied by the theta function, is in fact just one-dimensional space. And just by comparing the constant terms in the expansion, in this Fourier expansion, you see that it has to agree with something else that you construct by a different procedure, and that's a so-called Eisenstein series. And the punchline is you get an explicit formula for the theta series, which is completely arithmetical in nature now. So it tells you that if you look at the number of vectors in the E8 lattice of length square root 2n, that number is given by an arithmetic function of n. So, and that's exactly 240 times the sum of cubes of divisors of n. And it would be very hard to see this type of formula if you kind of try to work with the lattice directly. So that's a nice thing. And for us, the immediate corollary is actually that the E8 lattice, it has vectors of all lengths squared to n for all integers n. Surprisingly, it will play a very important role. Okay, so so this is unfortunately as much as I can tell about modular forms. Just to give you some idea of why things happen the way they do, these two transformation properties actually define, well, the action of SL2Z on the upper half plane. And this action has a nice, it has a nice fundamental domain. And in fact, you can kind of understand that because of these transformation properties, basically the behavior of the function is prescribed by its behavior on a compact Riemann surface. And that's where this finite dimensionality comes from. So this is just a picture showing how the fundamental domain tessellates the upper half plane. Okay, so I think I have to speed up a little bit. So now I want to formulate the main kind of tool, which is the linear programming bound. And that's where the Fourier analysis comes into the sphere breaking problem proper. And that's a very easy to prove theorem, but kind of a very deep theorem by Kohn and Elkis from 2004. And that tells you a way of producing upper bounds for the sphere breaking problem from a seemingly unrelated problem in Fourier analysis. So the formulation is, let's assume we have some nice Schwarz function. And the only properties that we want of it is it should be, after a while, it should be non-positive, and its Fourier transform should be non-negative. It's not immediately clear that there are any examples like that, but for the moment, we ignore this point. And the theorem tells you that if you have such an object, you get for free an upper bound for the packing density. And in particular, so if you normalize your size of the spheres so that the sphere is of radius r/2, then given such a function f, the upper bound for the density is the ratio of the values of f and its Fourier transform at 0. The proof of this theorem is extremely short, but I unfortunately don't have the time for it, but I will almost give it. In fact, for lattices, it's very, very easy to give. But what I want to talk about actually is there's a corollary, which is kind of striking. Well, The striking part about the theorem is actually it's not vacuous. So the theorem from the same paper is that if you have a function in dimension 8, which satisfies the above conditions for r equal to square root 2, and whose values at the origin are both 1, so both for the function and Fourier transform, then you would be able to prove that the E8 lattice is best packing. And that's kind of, well, it's now not a spoiler. So this is exactly what Marina proved. So that's her work in dimension 8. So she proved that such a function exists, and the best packing property kind of is an immediate corollary. And so I want to kind of give an indication of why this is a very strong condition, which a priori doesn't look so. So you're just asking for some inequalities for a function. But it turns out to be these are very strong inequalities. And here's the reason why. So let's just assume giving the statement of the theorem by Kohn and Elkis again. Let's assume such a function exists, and we just apply the Poisson summation formula to the E8 lattice. Then you can see that, well, if you start with f of 0, which is 1, the sum of all the other terms in the E8 lattice, it gives you some negative contribution because by definition f is non-positive outside the ball of radius square root 2. So you see that this quantity on the left here is bounded by 1. On the other hand, by Poisson summation formula, it's equal to the quantity on the right, and which actually all of the terms except the first one are non-negative, and the first one is 1. So you actually get a lower bound, which is also 1. So in particular, it tells you that f and f hat, they vanish on the full lattice. Well, it's again, it's lambda 8. And in fact, because you can rotate the lattice in any way you like, and you can repeat this argument again, even though we didn't assume any kind of radial symmetry, the function, if it exists, it has to vanish at concentric spheres of radius square root 2n. So that actually is a very strong condition. And as we will see, it's an incredibly strong condition. So, so let me just say one comment that we can assume that the function in their theorem is radial because if it is not, we can just average over all rotations. And if you draw the picture for the radial function, it looks something like that. So you have a function f, which is non-positive when x squared is 2 or higher, and it has zeros at all of the even integers. And in fact, because it has both inequality and vanishing, the zeros are all to second order except for the first one. And for the Fourier transform, we get exactly the same picture. All of the things vanish at even integers, and they have to vanish to second order because the function is non-negative. Okay, so this kind of just to restate what is going on, it tells you that among this long list of special values of your function, there's only one non-zero value, which, well, you don't know a priori. And what I want to say is there's kind of very, very rigid situation going on here. Okay, so let me switch a little bit to a topic which is deeper to in harmonic analysis, which is the so-called uncertainty principle. So, so the famous and kind of the titular uncertainty principle is the Heisenberg's uncertainty principle from quantum mechanics, which you can reformulate as a statement purely about Fourier transform. So it's a purely Fourier analytic statement. And it exactly tells you something about how well you can concentrate a function at the origin together with its Fourier transform. So it's like the precise version is actually is just this inequality here, which tells you that if you normalize your L2 norm of a function to be 1, then there is a limit to how well you can make both of the numbers on the left close to 0. And these numbers are clearly very small if your function is concentrated around 0. So this is kind of the exact, I mean, this is roughly the statement about position and momentum of a wave function. Sorry. And so there's several other statements in literature which are of similar nature, And you can kind of formulate a very general idea of what an uncertainty principle tells you. And that is, if you require very strong properties both for the function and its Fourier transform, most often, if your properties are strong enough, you actually only get the zero function. So one other example is the so-called Hardy's uncertainty principle, which also looks close to what I'm talking about. So it tells you that if you want your function to decay like a Gaussian, but faster than a certain type of Gaussian, and you require the same thing for the Fourier transform. Oh, sorry, this should be f hat, and this should be f hat. Then the function has to vanish. And so the discussion that we had previously with the vanishing of values at square roots of even integers actually also corresponds to an uncertainty principle, which looks a little bit different. So now we're saying we want a function which vanishes for all square roots of even integers to second order, and whose Fourier transform has the same property. And it turns out that if it's a radial function on R8 or R24, then it has to vanish identically. So again, we get some kind of an uncertainty principle. So the more precise version is the following result. In fact, so not just we have this kind of uncertainty principle, but we have a companion interpolation formula, which tells you exactly how to recover any function just from the information of these values. And so this is the part where actually one could get away without talking about this theorem at all, because the only function you need for the Cohn-Elkis theorem is b1 of x, and Marina's proof is just a direct construction of this function. But for what I want to talk about next, this is kind of conceptually a better point of view, because it kind of tells you that there's a very rigid analytic phenomenon behind the whole story. Okay. And I want to talk about, so I think I have to skip this part. There's an easier version of this type of Fourier interpolation formula, which doesn't talk about dimension 8, and it doesn't have values of derivatives. So you only take values at square roots of integers, and there is a similar reconstruction formula just for any function on the real line which is even. So this is our analog of radial functions in R8. And the formula is both conceptually easier, and actually it is it's both easier to state and easier to prove, which is why we proved it first. And so this is the second entry of modular forms into this story. And I want to say maybe just a little bit about how, not necessarily explaining why this whole thing works. So I just want to explain a construction of one of these functions appearing in this formula. So what one does is we want to construct a function which vanishes, it doesn't vanish at 0. It's a Fourier eigenfunction, so it's invariant under Fourier transform, and it vanishes at square roots of integers for all positive integers. And the construction uses the theta function of the integer lattice, and it's basically given by this formula here. And I just want to mention, so well, it doesn't necessarily give you an approach to proving the previous theorem, but from this formula, it's easy to verify both properties. So one of the properties is that these values should vanish, and that's because if you look at square root m in this formula, it's just a formula for the Fourier coefficient of the function theta cubed. And the second property is the Fourier transform is equal to itself, and that you just see by a computation if you change variables in the integral to -1/c. So it's a very simple calculation, and it kind of explains, well, why modular forms are relevant. In fact, they're much more relevant, but that's kind of a separate story. So what I want to finish with is a small discussion of kind of several conjectures related to this, which are a little bit more general. So instead of looking at sphere packing problem, one can consider more kind of more fine version of clustering or kind of a quantity which tells you how points are distributed in the configuration, and that's given by potential energy of the configuration. And you just have to think of it as a kind of sum of pairwise interactions between points, where each interaction is just a function of the distance. So I have to kind of skip the details. But the nice thing is you can, even though all of these formulas are terrible, for lattices, we're just talking again about the theta function. So for lattices, if you take Gaussian energy, then you're just interested in computing the values of the theta function for imaginary arguments. And there is a conjecture which kind of explains something about this dimension 8 and 24 business. So a much stronger property is true for E8 and Leech lattice. Namely, they're universally optimal. And what is universally optimal? It means that it has minimal energy for every Gaussian. And so this general interpolation formula that I just talked about actually allows you to prove universal optimality of the E8 lattice and the Leech lattice, which it turns out to be a much more difficult property. And in fact, so unlike the sphere packing problem, we don't even know the answer in 2 dimensions. So we don't know the answer to the conjecture that triangular lattice is the optimal way of arranging points for the Gaussian energy in dimension 2. And that's kind of a striking point. And so maybe I can explain more if there are questions about that. But I want to end on a very kind of strong conjecture, which to some extent, well, none of these conjectures explain why 8 and 24 work the way they do, but at least they explain that there is some general analytic phenomenon which is less sporadic. And so the problem is, let's go back to this Kohn and Elkis theorem and think about what happens in dimensions other than 8 and 24. So their theorem is completely general, and essentially it tells you that you want to find a function whose values at the origin are 1, both for the function and its Fourier transform. You want the Fourier transform to be non-negative, and you want the same vanishing, you want non-positivity outside a ball of radius r. And the goal is you want to make r as big as possible. So in dimension 8, for example, the best value of r you could get was square root 2. In dimension 24, it's 2, but in general, we have no idea. And there is only one other dimension where there's even a conjecture, and that's dimension 2. And unfortunately, it's open. So this is kind of, even though Kohn and Elkis approach should work for sphere packing in 2 dimensions, which is not hard, we don't have a proof of this type. But there's kind of a general thing that happens in every dimension, and then I'll stop here. So it turns out that if you try to solve this problem and you do it with numerically, there's some kind of behavior which emerges, which is not very easy to explain. And that to some extent, it's the counterpart of the miracles that happen in dimensions 8 and 24. So there's something happening in all dimensions. And first part of it is that there's always a unique solution to that problem. So there's a unique value, unique function f, and the precise value of r for which it is optimal and no other solution works. And in fact, the function that it attains it is a nice Schwarz function. So far, so good. Then if you look at the values of points where the Fourier transform of that function vanishes, it's always a big infinite set, roughly of the same type as we had in dimension 8. So it's going to be a collection of numbers Rn, where the nth one behaves roughly like square root 2n, possibly with a shift. And the surprising part is actually, if you look at the values where the function itself vanishes, it is essentially the same set. And the final part, which is the most kind of speculative, is that once you have this setup, you have a similar interpolation formula to the one which helped solve the story in dimension 8 and 24. And now there's absolutely no idea of how it connects to modular forms. But maybe, so one final thing I'll mention before I stop is that in addition, there should be kind of a magical theta function that plays well with the optimal solution for the problem in this conjecture. And the theta function should behave essentially just like the theta function of a lattice, except it's almost certainly not a theta function of any lattice, because if it were the case, we would have another solution of sphere packing problem in that dimension. But somehow, well, the miracle remains that in dimensions 8 and 24, these analytic problems have a solution which is a nice modular form. Okay, I think I should stop here and maybe leave some room for questions because I'm running over time. Okay, thank you.
Okay, thanks to you, Danilo. A big online clap. So now there are some room for questions, so any of the attendees are able to unmute themselves and ask the questions directly or post the questions in the chat and we read them. So feel free. I think you can all unmute yourself. Otherwise, let me know.
In the meantime, first, thank you for this talk. I have more a curiosity than a question, but as you know, in recent days, there are like news saying that AI has been used to solve some type of unsolved problems and so on. So I was wondering if this type of conjectures have been tried to solve them with AI, or even if you said that there are some computer systems that have been used to have some proofs, but they are not able to be understood by a person. So if you have tried to understand the logic behind these proofs with some kind of these tools or something like this?
That's actually like an excellent question. Thank you. Well, okay, so I should say a few comments about what I said here. So there's several computational proofs. So this most recent one is pure computational proof. As far as I know, has nothing to do with AI. It's just a very, 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 very heavy calculation that one had to do. So if you want, so like basically the keyword is the so-called perfect lattices and the Voronoi algorithm. So people just managed to implement it in dimension 9, and it's a very kind of difficult thing to do. But it's completely a classical calculation without any machine learning techniques or whatsoever. And again, these two results are also, as far as I know, have had no kind of input. Well, they kind of predate the current wave of machine learning frenzy. But there certainly is a lot of interest. So I am aware of at least a few kind of recent attempts to use AI to discover better packings in high dimensions. And there's very good reason why this should be possible because, well, first of all, not many people tried very hard, but also people are not very good at discovering unstructured kind of semi-random solutions. And there's very good reason to expect that machine learning will be better at some point. It's just that I think up to this point, there may not have been any improvements to the state of the art, not for the sphere packing problem itself, but there's a related problem about spherical codes where I think actually there have been some like AI found examples in a recent paper. So in principle, one would expect that these difficult kind of search questions of searching very complicated configuration spaces are maybe from the onset are better suited towards machines than to humans anyway. So what kind of the special thing is that humans have discovered the most symmetric situations. But presumably, if you go to like dimensions beyond 24, there would probably be many new configurations which are better than what we know, which you can only access by just computation. So yeah, but as far as I know, and I may actually be wrong on this, so there's not yet any new configuration for the sphere packing problem that people found with AI. But I mean, my information could already be outdated, so you should also check. So you can
Okay.
also check with AI again.
Thank you,
Thank you.
Belén, for your question, and also Danilo for the answer. So are there more questions in the audience? Yeah,
Yes.
you can.
Yes.
Hi. Thanks for a nice talk. I have a question whether there is some generalization outside of Euclidean spaces. So let's say Riemannian symmetric spaces or something like that.
Yes, that's actually so it's a lot less kind of systematically investigated. So it depends on how far you go into the how fancy you want your symmetric spaces to be. So first of all, for the natural next candidates are the hyperbolic space and the sphere. And for sphere, it's equivalent to the question which people call spherical codes, and it's very well studied, and there's a lot of information known. And actually, that was one of the examples where there is a recent work where people could use AI to find a better construction in some high dimension. So the spherical case is very well investigated. In a sense, it's better investigated than the sphere packing problem itself because it's compact. The hyperbolic case is kind of on the opposite end. It's a lot more strange because actually even defining what you mean by density is not obvious. The problem is like in Euclidean case, you always kind of ignore what happens on the boundary of the sphere because you can always I mean, it's a small portion of the volume in a fixed dimension. And in hyperbolic space, it's no longer the case. So like epsilon neighborhood of the boundary contains a constant proportion of the volume. So you can't ignore this behavior. And actually all of the simple proofs which work in Euclidean space, they just don't work. And it's even kind of a problem to define what you mean. What is a sphere packing density? The problem itself is well defined, at least for lattices, which is an extremely interesting part of the whole story. So if you just ask about lattices acting on hyperbolic spaces and take sphere packings which are invariant under such actions, it's a perfectly legitimate question. Unfortunately, I don't think I know even a single result of that type in dimension above 2. But it could be that actually there is something that is known. And if you go kind of beyond that, you do some like elliptic spaces, or you do Grassmannians or whatnot. I think there's kind of diminishing, rapidly decaying number of papers in those directions. So if for projective spaces, there's relatively there are quite a few interesting things for complex projective spaces. That's actually connected to it's connected to quantum information theory. There's some interesting results in that direction, but I think even for Grassmannians already, I don't know. I know there are some results. I don't know anything particularly striking there. So yeah.
Thank you. Actually, complex Grassmannians are like my main interest because they have applications in wireless communication. But yeah, we kind of hit a roadblock outside of this rank 1 case, or outside of complex projective case. I guess it's because of the super rigidity there. There are just not.
I think I'm only aware of there are some very surprising and interesting results about packing problem in complex projective spaces. So that I know. And there's kind of some deep connections to number theory, but I don't know anything about Grassmannians, unfortunately.
Okay,
And also, real projective space is a lot worse. So there's some results in that as well, but it's a lot more sporadic. Whereas for complex projective space, there are some very regular sequences of objects which people conjecture they exist in all dimensions. But as far as I know, it's not yet proven that they do.
Thank you.
Yeah.
Thank you very much. So there is also a question in the chat. So I don't know if Florian Osman want to say it. Otherwise, I will just read it. And yeah, if you want to join the discussion, then you can unmute yourself. So thanks for the talk. I have a small question. All the dimensions 1, 2, 3, 8, 24 can be written as 2 up to P3 up to Q for PQ greater or equal than 0. So the problem somehow seems to be connected to the numbers 2 and 3. Is this just random coincidence or something deeper behind?
I don't necessarily know if, well, it's certainly not coincidental in the sense that dimension 24 has something to do with okay, so there's a story about 12 and 24 in the modular form business, and that has to do with the kind of the Euler characteristic of the modular curve. And that only involves numbers 2 and 3. And in fact, the fact that you have Leech lattice is connected to the fact that the first cusp form has dimension weight 12, which is what people used to call dimension minus 24. But so it's true that actually 2 and 3 appear naturally, and one could argue a little of the story has to do with the fact that so these special lattices are often even unimodular lattices, and they kind of see the SL2Z story. So in a sense, 2 and 3 torsion are natural in that story, and you can kind of expect that powers of 2s and 3s are also kind of more special. But unfortunately for like 1, 2, and 3, I mean, the first number, which is not power of 2 times power of 3, is 5. So it's more about the fact that it's like a low dimensional story, and all of the low dimensions are products of 2, 3. Well, 5 is not, but also for 5, there is no kind of nice story to be told. We don't have a proof, and also there's infinitely many different objects which have the same density. So there's nothing really special in dimension 5. But also, like, for example, 6 also doesn't have any nice properties as far as we know, but the 6 is products of 2 times 3. I mean, it seems some of it is actually not numerology. So I think this connection to modular forms, and you clearly see the number 12 there. But as far as I know, it's kind of it's not really easy to see how to use it in any meaningful way. So one could imagine also that something special happens with prime 5 in some different setting, but I just don't know. We have too little data to kind of extrapolate from here.
Okay, thank you, Danilo. Florian says thank you too. So are there small questions around there, or otherwise we let Danilo leave? Okay, so yeah, thank you again, Danilo, for your nice talk and for staying with us today. Thank you very much.
It was quite fun.